Hi, my name is Adele, and in this video, I've decided to talk about the first law of thermodynamics and its applications. But before I can explain the law, we must cover a few other topics that together form the first law of thermodynamics. So, the first law accounts for four different types of energy. First, there's internal energy, which is denoted by U, and it's the microscopic energy stored in the molecular structure of a substance. It includes both kinetic and potential energy, and any changes in the internal energy are a result of temperature changes and phase transitions. There's also kinetic energy, which is denoted by Ke, and it's the energy due to motion. There's also potential energy, which is denoted by Pe, and that is the energy due to elevation in a gravitational field. And finally, there's enthalpy, which is denoted by H, and that is the essential in open systems, and it's equal to the internal energy plus the pressure times the specific volume. A first aspect to the first law is heat, which is denoted by Q, and it's another key form of energy transfer. The methods of energy transfer include conduction, which is the energy transfer through a solid due to a temperature gradient. There's convection, which is the energy transfer between a solid surface and a moving fluid, and radiation, which is the energy transfer via electromagnetic waves. Specific heat represents the energy required to change the temperature of a unit mass by 1 degree Celsius. It's classified into two different types. First, there's specific heat at constant volume, which is denoted by CV, and that is used when the volume remains constant, meaning that no work is being done. For ideal gases, the change in internal energy is equal to the specific heat at constant volume times the change in temperature. The second is specific heat at constant pressure, which is denoted by Cp, and that is used when the pressure is constant. For ideal gases, the change in enthalpy is equal to the specific heat at constant pressure times the change in temperature. That can be related to the energy analysis in turbines and compressors, for example, where heat would be equal to a change in enthalpy, and that is also equal to the specific heat at constant pressure times the change in temperature. The second main aspect of the first law is work. Work is a major form of energy transfer in thermodynamics, and there are several types of it. To define work, it's the energy transfer in or out of the system associated with a force acting through a distance. So first, there's boundary work, and that occurs when a gas expands or compresses. Next, there's also flow work, and that is the work required to push a mass in or out of a control system. There's also shaft work, and that is the work done by rotating devices, and it occurs in turbines, pumps, and compressors. Additionally, there's spring work, and that is the elongation of a spring under the influence of a force. And finally, there's electrical work, and that is done when electric current flows through a resistance. There are a few important things to know when discussing work. So first, if there is no movement, there is no work. Moreover, work is a means of transferring energy. It does not refer to what is being transferred. And finally, but most importantly, work is not a property of the system. There are also many types of processes in thermodynamics, but there are three worth noting when talking about the first law. So the first is a polytropic process, and that refers to the thermodynamic process in which a gas undergoes compression, which would be a decrease in volume, or expansion, and that would be an increase in volume, while following the polytropic equation. So the polytropic equation is defined as a product of the pressure and the volume to the n, and that's equal to a constant. In this case, n is the polytropic exponent, and that depends on heat transfer conditions. For this type of process, n is not equal to 1. And the work done by this process would be equal to the product of the outlet pressure and volume minus the product of the inlet pressure and volume, and all of that is divided by 1 minus the polytropic exponent. A second process is isothermal process, and in that process, the temperature remains constant. So for this, the polytropic exponent is equal to 1. And the work done by this kind of process is equal to the product of the inlet pressure and the volume and the ln of the outlet volume over the inlet volume. Lastly, there is the isobaric process, in which the pressure remains constant. The polytropic exponent for this kind of process is equal to 0, and the work done is equal to the pressure multiplied by the difference in volume. So now, having defined all the kinds of different heats and works, we can now define the first law of thermodynamics, which is based on the conservation of energy principle. So essentially, the first law states that the change in a system total energy is equal to the net heat transfer into the system minus the net work done by the system. And so in the equation, refers to the heat to or from the system, and W, the work done by or on the system. There are important sign conventions to consider when using the first law of thermodynamics, which may seem counterintuitive. So the heat that is added to a system would be positive, while the heat that is lost from a system would be negative. On the contrary, the work done on a system is negative, while the work done by a system is positive. So there's actually a few different versions of the first law of thermodynamics depending on the kind of systems it's being used on. So for example, for a closed system, energy can only be transferred as heat or work. So we get the regular um, version of the first law. But for open systems or control volumes, energy transfer can also include mass flow. And for steady flow systems, the first law is equal to 0. So therefore, um, 0 would be equal to the difference between the heat and the work. So for both open and steady state systems, so the last two, um, the first law can be expressed to account for enthalpy, kinetic energy, and potential energy changes. And that comes really handy for steady state equations. And you can see it right here for open systems. And finally, to conclude, there are many different applications of the first law of thermodynamics in engineering. So one big application that we see in problems is nozzles, which increase velocity by decreasing pressure, and diffusers, which increase pressure by decreasing volume. Another is turbines, which extract work from a fluid, and compressors, which require work input to increase pressure. It can also be applied to throttling valves, who reduce pressure without significant work or heat exchange. And lastly, heat exchangers, which are used to transfer heat between two fluid streams without mixing them. Thank you.